Beginning with the serum chemistry values for the 4 main ions important for biological excitability, we have a panel that shows you the normal values for sodium, potassium, chloride, and calcium. These are the 4 ions we'll work with as we describe membrane potential and excitability. In the next slide, you see the picture of a neuron on the left and some ion values on the right in a box. The first component that we're going to look at is the cell body. In the cell body, all 4 of these ions play a role in membrane resting potential and membrane excitability, which will eventually lead to an action potential. In the second of these neuron slides, we're focusing on the axon itself. The axon has permeability to sodium ions and potassium ions, but not to calcium and not to chloride. In the context of the axon terminal, in the following slide, you'll see that calcium ions now are featured and play a role, and potassium ions are still important. So in the next slide, we're going to focus on the movement of potassium through the cell membrane. Notice that the intracellular number of potassium ions is higher than in the outside. And there's a channel, a little protein hole in the membrane, that's going to allow potassium to flow out of the cell now that it is open. Why is potassium flowing from the inside of the cell to the outside? It's due to the concentration gradient. The concentration of potassium is significantly higher inside the cell compared to outside. This difference in intracellular versus extracellular potassium is called a chemical force. When a potassium ion leaves, the potassium ion having a positive charge leaves the cell, it leaves the intracellular side 1 charge more negative than before and 1 charge more positive on the other side. So the flow of potassium is not just a chemical force, it's also generating an electrical force. In the next slide, you can see this more clearly as it leaves behind an overall negative charge on the inside of the cell. Notice that by being more negative inside, it will actually generate a counterforce, a force to attract potassium to flow back into the cell. However, the chemical gradient is much more massive compared to the electrical influence on this one single potassium ion. And so potassium ions will be flowing out of the cell, and a very limited number will be returning through the channel back into the cell. Notice that this part of this slide is depicting the electrical force or the electrical gradient. These 2 countervailing forces, the chemical force of the concentration gradient and the electrical force generated by the difference in the extracellular versus the intracellular charge, are modeled by something we call the Nernst potential, which is shown in the next slide. The equation for the Nernst potential is shown on the right-hand side, and it is intended, and the diagram on the left is showing you the flux of the ions. Remember, potassium is high inside and low outside. That's the chemical portion of the equation, and that is shown by the log of X inside over X outside, where X would be potassium ions. The electrical component is shown by the constants in the middle. These are the R, the gas constant, T, the temperature, in degrees Kelvin, the valence of the ion, in this case 1, and Faraday's constant. So there are 2 components to this work equation. There is the work of the chemical gradient in one direction and the electrical gradient in the other. Together, the chemical force for the potassium ion to leave and the electrical force to retain it have potassium flux at an equilibrium. That equilibrium, E, is modeled as a potential in millivolts. So the electrical potential at which potassium efflux and influx are equally probable is known as the equilibrium potential for potassium. And it can be calculated using this equation. In thinking about the Nernst potential for an ion such as potassium, we are focusing on that point where potassium influx and potassium efflux are equal, and that's called the Nernst potential. That has importance because it governs the direction in which ions will flow as much as the concentration gradients. In fact, the concentration gradient is a part of what gives us this electrical potential. So the electrical forces that are coming from the gas constant, the temperature, the Faraday constant, and the valence of the ion all collapse because it's typically not changing it's typically not changing with time. These constants collapse to a value of minus 61.5 millivolts. And that's the electrical component. On top of that electrical component is the concentration gradient, which also is going to influence the final equilibrium potential. Ions flowing out of the cell into the extracellular space leave the cell, inside of the cell, more negative. So that's also contributing a negative value to the overall equilibrium potential. So in this slide, you'll note that the equilibrium potential for potassium is roughly minus 90 millivolts. That's the potential at which the potassium ion is as likely to leave the cell as it is to enter the cell. And the main force that you need to be concerned about, because it relates to the serum chemistry, is the concentration of potassium inside versus the potassium concentration outside. How a change in the extracellular potassium, which is the value that you see in your serum chemistry panel, will influence the Nernst potential for potassium and in turn influence the resting membrane potential of the cell is important, because in the conditions such as hyperkalemia, when extracellular potassium levels are high, you're going to affect both of these values, both the Nernst potential for potassium and eventually the resting potential for the cell. In the case of elevated blood potassium, otherwise known as hyperkalemia, the increase in the number of extracellular potassium ions has an influence on the Nernst potential. Notice the concentration gradient is reduced. It's not as steep. There are more extracellular potassium ions than in the normal, and so there is reduced flux from the inside of the cell, reduced efflux of potassium ions to the extracellular side. This means that there's also, because of this more shallow concentration gradient, an increase of potassium ions that are likely to be returning to the inside of the cell. These two factors, the reduction of efflux of potassium and the increase of influx of potassium, cause the Nernst potential to become less negative. In other words, to depolarize the membrane.